Good morning, folks. If the four elements are the correct theory of everything, then we should see them at the heart of all science. But all of science is founded in information, so information itself is fundamental. The four are the archetypes of all processes, so information processing must contain the four, and only the four. To have a computer must require the four elements, and it does, of course. So I believe that the Turing-Machine proves the four elements. It's the simplest conceivable universal computer, and it's the four elements. To be fair, you can have it's kind of in a class of the simplest conceivable universal computers. There are others that all kind of have similar characteristics. They all have the four elements in them. In general, and this is my little rant, is I do believe that Western thought and science and philosophy has been rendered largely impotent by the removal of the concepts of the Tao and the four elements from our culture. Far from being a primitive superstition, they are the real theory of everything and the true framework of reality. And science really threw the baby out with the bathwater when they discarded the idea of the four elements. So computing follows the laws of the Tao and the four elements, and here are some examples of duality in computing. Of course, it's based on binary, which is the most obvious one. And 0 is yin and 1 is yang. A program consists of data and code, and data is yin, it's the matter, and the code is the spirit, it's the active part of the program. You have input and output is yin because it depends on the input, which is the driver. A computer has hardware and hardware is yin because it's matter, and software is spirit, it's electricity. And software, is an application, and it runs on an operating system, and the operating system is the provider to the application. It's the framework in which it exists. So all relationships have a Taoist relationship. All relationships are the Tao. So there's probably plenty of other examples in computing of dualities, but they would fit into the Tao, because everything does. So a Turing machine program it's very interesting because it reveals its true nature, what it's all about, how you write the program. It defines the computer, really, because you don't actually build these things anyway. They're only a theoretical, conceptual computer. It's an abstract thing that people use to study the idea of computing. So a program for a Turing machine is written as a table, which is a two-dimensional list. In the example below, there are two axes, of course, and we have current state here on the x-axis and input symbol on the y-axis. If you don't understand how a Turing machine works, it's not entirely necessary, I don't think, to understand what I'm getting at, but if you'd like to, go to Wikipedia, it's got an explanation. So basically this is a two-dimensional machine. Its entire behaviour can be described as a two-dimensional matrix, which is this table here. And so it's defined by the four elements, which are the 2D water level of reality, water element level. And it corresponds to action, power and work. And the Turing machine is the simplest universal computer, and computing is work. So it all ties in. So in this example program, we can see that each cell in the table is a single instruction. So if we look at this cell here, for example, if we are in current state A, and we receive tape symbol 0, then we would execute this instruction. And the instruction consists of three things, and this is the bare minimum that it has to in order to function. We have a write symbol, so it will write a symbol back to the tape, it will move the tape either right or left, and it will determine what the next state of the machine is in. And so, okay, that's it. So here the current state is the yin axis because it's passive. The state has already been set by the previous instruction. And the input symbol is the yang axis because it's active and we have to read it in this instruction. And as a note, most if not all 2D graphs have an active and passive axis. One value drives the equation and the other is calculated. So as an example, to try and enable you to visualise how you would use this computer, is a dancing robot, because it's kind of easy to visualise. So if you imagine that each of the states is a different pose or body configuration for the robot, and then each of the inputs would be an instruction to move to a new pose, but with the option of changing the pose setting for the current instruction at the same time. So the robot could constantly rewrite its own program as it's running, and so create a dance which never repeats. It would be a program using kind of mathematically induced chaos by a continuous iteration process, which is just basically repetition of the same thing. So there are 4 parts to the instruction. Each instruction in the program, each cell in the table, has 4 necessary parts. It can't do its job without all 4. And they are conceptual requirements for the function of a universal computer, and they're defined by the 4 elements. They follow the yin direction of earth to fire, yin to yang, from matter to direction, and it's the same pattern as solving a problem or forming a mind. So here's my table. We've got the 4 elements down here, earth to fire. We've got a description of what they mean. So earth is the location in the table. It's the current state and input symbol, and it defines our location in this table, the 2 coordinates that we need to know which instruction to run. The water element, the next step, is action, and so it's the right symbol function. The air is the law. It's the choice between this or that, and that is move tape left or right. And then fire is the will or direction, and it's the next state. And this corresponds to making a decision in the following way. So the first step of making a decision is to gather information on a situation. The next step is to refine and reject information by thinking. You compare and find correspondences and contradictions in the data, and so on. And then from that you can form an analysis, which is the law. It's your idea of what's right and what's wrong, true and false. So you gain understanding. And then once you have understanding, you can make a decision. So all computing processes follow the same pattern. And the Turing machine has been very well studied mathematically and conceptually. So it stands, in my opinion, as a logical and mathematical proof of the necessity and existence of the 4 elements. So just to elaborate a little bit and talk about another kind of aspect of super simple computing. There are things called 1 instruction set computers, which people have created for fun. It's an abstract machine that only uses 1 instruction. It's capable of being a universal computer in the same manner as traditional computers, but it's only got 1 instruction. And you can see that on Wikipedia if you're interested. So this is a class of computers that people have explored to try and understand the limits of computing. It's purely for fun, they're not practical at all. But again, it shows we need a minimum set of things in order to do computing. 2 examples of the single instructions you can use if you're interested are subtract and branch if negative, or subtract if positive, else branch, and that kind of form of instruction. And so they correspond to the 4 elements in the same order as before, as follows. So earth is location, it's in the instruction, and it's the current position or the instruction pointer for the program. Water is action, so it's the subtract A from B function. Air is the law, so it's the branch if B is negative. And fire is the branch to option or aspect. And note that A and B are registers, their memory locations, just for information. And again, so it follows the same pattern as the Turing machine because it's attempting to do the same thing. And so the 4 elements thus define a universal computer. I hope you found that interesting, guys, and it was clear enough. If you've got any questions, please ask. Thanks for watching. I'll catch you soon. Take care.